The manufacturing process of an industrial-grade, single-piece cast iron skillet requires precise metallurgical calculations and controlled thermodynamic transformations. The operation begins at the raw materials automated stockyard. The primary metallic charge consists of high-purity pig iron, 45%, sorted low-carbon structural steel scrap, 40%, and recycled internal iron gates and runners, 15%. To adjust the final material specifications, chemical inoculants and ferroalloys, specifically ferrosilicon, Fe, and ferromanganese, Fem, are systematically added to the mix. This precise chemical ratio is engineered to control the carbon equivalent, CE, value. Aiming for a target of 3.8% to 4.2% carbon, and 1.8% to 2.2% silicon. Silicon acts as a powerful graphite stabilizer, preventing the formation of hard, brittle iron carbides during rapid cooling phases. Manganese is monitored to neutralize the detrimental effects of trace sulfur impurities. The solid metallic charge is loaded via an automated vibrating conveyor into a high-capacity coreless medium-frequency induction furnace. The furnace operates using a 12 megawatt electrical power supply. A high-frequency alternating electrical current passes through heavy, water-cooled copper induction coils that wrap around the exterior of the alumina-based refractory crucible. This current creates an intense, rapidly alternating electromagnetic field. As the magnetic flux penetrates the solid steel and iron scrap, it induces localized circulating loops of electrical current, technically known as eddy currents, directly inside the metal structure. Due to the natural electrical resistance of the iron substrate, these eddy currents dissipate electrical energy into pure thermal energy. The temperature rises rapidly from the inside out without the use of direct fossil fuel combustion or external gas burners. When the temperature hits the eutectic milestone of 1.147 degrees Celsius, the alloy system undergoes a solid to liquid phase change. The solid crystal structures collapse into a turbulent molten state. The induction furnace continues to inject energy, superheating the molten bath to an optimal pouring temperature of 1.480 to 1.520 degrees Celsius. This high thermal level reduces the kinematic viscosity of the liquid metal, optimizing fluid fluidity for subsequent mold penetration. At this temperature, reactive atmospheric oxygen forms an undesirable layer of metallic oxide impurities on the surface, known as metallurgical slag. If included in the final casting, slag creates structural defects and air voids. A technician uses a high-temperature refractory skimming tool to drag the dense slag out of the furnace bath, leaving a clean, white-hot molten metal surface. Once the chemical composition is verified via optical emission spectrometry, OES, hydraulic cylinders tilt the induction furnace along its primary axis. The liquid iron flows into a preheated, refractory lined transfer ladle. The ladle maintains the thermal stability of the molten iron at 1.420 degrees Celsius as it moves toward the automated pouring station. Simultaneously, the automated molding division prepares the green sand molds using advanced Flaskless vertical molding machinery. The molding medium is designated as green sand due to its moisture content. The sand mixture comprises high-purity silica sand, 85 to 89%, sodium bentonite clay binder, 7 to 10%, pulverized sea coal additive, 2 to 4%, and water, 2 to 3%. The bentonite clay absorbs water, creating a cohesive gel matrix that coats each individual silica grain. Under mechanical compaction, these grains interlock, providing high compressive mold strength. The sea coal additive undergoes thermal pyrolysis when exposed to molten metal, creating a microscopic protective hydrocarbon gas cushion that prevents the liquid iron from physically fusing with the silica sand, thereby improving the surface finish. The green sand is blown via high-velocity compressed air into the molding chamber of a vertical flaskless molding machine. Two precision machined tool steel pattern plates, one representing the internal basin of the skillet, the other the external profile, compress the sand under 150 bars of hydraulic pressure. This swift cycle creates a dense, self-supporting sand mold block containing the negative geometry of the product. The machine ejects these blocks continuously onto a high-precision linear conveyor line, where they are pressed tightly against each other. The junction between each consecutive block forms a sealed internal casting cavity, equipped with an engineered pouring cup, downsprue, and runner gating system. The transfer ladle aligns automatically with the moving sand mold string. An automated laser sensor detects the pouring cup position, triggering the bottom pour nozzle of the ladle. The liquid iron enters the gating system under controlled laminar flow conditions to prevent sand erosion. As the iron occupies the casting cavity, the moisture in the green sand flashes into steam. The natural microscopic porosity of the compacted silica sand allows this high-pressure gas to escape outward through the mold walls, preventing gas entrapment and subsurface blowhole defects within the skillet body. The filled molds advance down an elongated cooling conveyor for 45 minutes. This slow, regulated cooling rate allows the carbon atoms to separate from the solidifying iron solution, forming interconnected flakes of pure crystalline graphite within a pearlitic metallic matrix. This microstructure defines the material as gray cast iron, grade 200, Gg20. The graphite flakes give the skillet its superior thermal mass capacity and excellent heat retention characteristics. The cooled mold string reaches the high-frequency mechanical shakeout grid. Violent directional vibrations break the weak clay bonds, causing the sand mold to disintegrate into loose particles, which fall through the grid into an underground sand reclamation and reconditioning system. The raw, hot skillet castings emerge onto the vibratory line, containing solid metal gate remnants and burnt sand. A robot lifts the castings into a continuous shot blasting chamber, where high-velocity steel shot pellets remove all residual sand and oxide scale, exposing the raw gray metal. The desanded skillet castings enter the finishing automated cell. Each raw casting possesses a thick metal gate vestige at the rim and sharp flashing lines along the parting plane where the two sand molds met. These geometric imperfections must be removed mechanically to meet dimensional tolerances. A 6-axis industrial robotic arm equipped with pneumatic active force-controlled grippers secures the skillet. The robot executes a pre-programmed CNC path, presenting the outer edge of the skillet to a heavy-duty, variable-speed abrasive grinding wheel. The robot's sensors monitor and adjust the physical contact force in real time. This precise force regulation prevents excessive frictional heat generation, which could cause localized thermal cracking or martensitic microstructural changes in the gray iron. The grinding wheel cuts away the gate vestige and flushes the flash line, rendering the rim smooth and safe. The skillet is transferred to the interior surface machining center. Raw sand cast surfaces are naturally textured to improve the culinary performance and enhance tactile smoothness. The interior cooking basin is milled. The skillet is clamped into a rotating hydraulic chuck spinning at 800 RPM. A computer-controlled machining head fitted with silicon carbide abrasive wheels descends into the basin. The head moves along an automated spiral path from the center out to the sidewalls. This process removes the rough surface layer, exposing a smooth finish characterized by fine, concentric micro grooves. These microscopic grooves are engineered to a specific roughness average, raw, value, creating an ideal texture that allows liquid oil to anchor via capillary action during the seasoning stage. Following machining, each skillet undergoes non-destructive quality control.
Under intense
a technician
heat, the
performs an
vegetable
acoustic
oil layer
resonance inspection
carbonizes
by
and
striking the
polymerizes,
center of the
bonding
skillet with a
the
calibrated nylon hammer. An unblemished, fully dense gray iron casting exhibits a distinct, clear, high-frequency acoustic ring. If the internal structure contains hidden gas porosity, shrinkage cavities, or microfractures, the acoustic wave is dampened, producing a flat, distorted sound. Skillets with anomalous acoustic profiles are rejected and returned to the melting yard. Skillets that pass are hung on an overhead line and passed through a multi-stage ultrasonic cleaning tank containing a hot alkaline degreasing solution to strip away all metallic dust and machining lubricants. The clean, raw iron skillets proceed directly to the industrial seasoning line to receive a permanent, natural protective barrier. Without this step, raw iron reacts with atmospheric moisture and oxidizes into iron oxide, rust, within minutes. The factory utilizes an organic, high polyunsaturated fat vegetable oil, specifically kosher-certified flaxseed oil, to engineer a non-stick coating through lipid polymerization. The skillets pass through a preheating oven that elevates the metal temperature to 180 degrees Celsius. This preheating phase drives off trace moisture and expands the microscopic pores of the iron surface. The hot skillets enter an automated electrostatic spray booth. The atomized flaxseed oil droplets are passed through an electrode array, giving them a high-voltage positive electrostatic charge. The cast iron skillets are grounded to a negative potential. The electrostatic attraction force